In this video, we're going to look at a short program, and the main purpose of it is just to sort of play with vectors in R, and the subject will be cosine similarity. So cosine similarity is you have some vectors representing something, answers to questions that may be numerical or something like that, but you have two vectors of equal length, and then you want to know how similar they were. So if they were somehow the answers to survey questions and you had two samples, you might want to know how similar were that set of responses. Okay, so just here's the Wikipedia page on cosine similarity. Uh, in data analysis, cosine similarity is a measure of similarity between two non-zero vectors defined in an inner product space. Okay, so here we go. So I just have two vectors. I made them of length 5, and so this is I am using assignment in an assignment statement in R. I'm using the equal, though you can also use uh, like a notation, like an arrow kind of a notation, or you can spell out the word assigned. I'm used to just the equal, so that's what I'm going to be using. There is this little c that sort of is used to when you are sort of establishing a vector. I think in R they say it stands for concatenate. I find that word confusing because I think of concatenation as a string thing. So, but anyway, it's a little c and then parentheses and then value separated by commas, and we do want the two vectors to be of the same length. So here I have some A and B, just numbers I happen to type, whatever they are. Okay. So let's run A and B. There we go. So here are my A and B over here. Now, if you take the product of two vectors, you're going to get another vector. And that vector is going to be, I'm going to take the first element of A and multiply it by the first element of B. And that'll be the first element of the product. And same thing for the second. I'll take the second element of A and this multiply it by the second element of B, and that'll be my second element of the product. So that's what we mean by a product of vectors here in R. I didn't want to do that. I wanted to run it. There we go, run. So we see here the product. So the first element of A was 2 and B was 1. And so the first element in the product is 2 times 1, which is 2. The second element of A is -4. The second element of B is 2. So the second element of the product is -4 times 2, or -8. There we go. Now to get what we call the dot product, we're going to just add up all of the elements in the product. So we can use, there is a sum method here. And there are libraries. I just tend to work in like I don't know, raw R, sort of whatever it gives me. But there are libraries where there will be, so I'm combining a multiplication and a sum to get the dot product. But there are libraries that will indeed just have a dot product defined. But so I tend to roll my own, especially because my purpose here is to sort of teach introductory R. So who wants to bring in a library that just does everything for you? Okay, so I'm adding up all of the elements. I'm going to add 2 plus -8 plus 15 plus 6 plus 2 and run that. So now I'm getting, so that was 17. That makes sense. 2 and -8 is -6, canceling this 6, the 15 and the 2, 17. That makes sense. Okay. So I'm working my way up to this thing called the cosine similarity. And part of it is there's sort of a numerator and a denominator. Do I still have that up? It is the dot product, the code. So we take the dot product, which is what we were just getting. This is another way to think about the dot product. Um, So the dot product can be sort of, I don't know, the first component of A times first component of B, for second component of A times the second component of B, add those all up. That also happens to be, in a way, the magnitude of A times the magnitude of B times the cosine. And then there's the cosine of cosine similarity. Um, so that's another sort of geometric way of interpreting where that theta is the angle between the two vectors. So you can be in some vector space and measure an angle between them. So this would be in two and three dimensional space, sort of like you can sort of picture it, sort of two vectors pointing up somewhere, and what is the angle between them. And so there are these two ways of interpreting, uh, of getting and interpreting a dot product. And then we want to just get this cosine out of it. And then cosine, as we know, is a trigonometric function that varies between -1 and 1. That's what we want. So this idea of similarity won't depend on how big the vectors were, but just be some number between -1 and 1. And so we're going to get to the cosine of similarity, we're going to divide by these magnitudes. So there we are. And then it's showing you down here that the magnitude of A is really sort of the square root of the dot product of A with itself. So this is A1 squared, or you can think of this as the dot product of A with itself, and then take the square root of it. So I took A times A, took the sum of it, and took the square root of it. That's my magnitude of A. So I did that for um, A and B. And again, I'm just sort of showing you things you can relatively easily do in R with vectors. So in older programming languages, all these vectors, you would be looping to do all these things. Um, defining a sum, looping over and keeping track, adding, appending the sum or adding the sum as you go along. So we had A and B, we took their product, we took the sum of that product, that gave us the dot product. We sort of repeated the same thing with the dot product of A and B with itself, with A with itself and B with itself, and then took the square root of that. So imagine somehow, I like to, think of these things as maybe having some unit, and then we want the magnitude of A. So if these were all somehow like meters or something like that in some physical space of distances, then we want the magnitude of A to have the same units as A to be meters. And so here you have A squared, so you need the square root to undo that. Okay. So we had the product, we had the vectors, we had the product, we summed it, we had the dot product, we repeated that process and threw it a square root, we got the magnitude of A and B. Now we're doing this, finally, we're ready for this cosine similarity. We divide the dot product of A and B and divide that by the magnitude of A and B. So both the magnitude of A and the magnitude of B are both in the denominator. And so I always like to have my parentheses around my numerators, or I only had one thing in my numerator, so I didn't need parentheses, but just to make sure I'm doing that both of these things it's being divided by both magnitude of A and magnitude of B. And so I'm going to run that. Okay, and here is the cosine similarity, and this is some number 0.4887 in this case, just some random example. But this is an idea of how, if we're thinking again of these two vectors as pointing in some space, uh, how similar are they in their direction? So one would be sort of completely aligned, -1 would be pointing exactly opposite, and 0 would mean that the vectors were sort of pointing at right angles. They're sort of orthogonal, as we say. Okay. So I just had some examples here. So I'm going to bring in a B here, which is just twice of A, so they're really pointing in the same direction. So if I run the whole thing again, now my cosine of similarity should be 1. These two vectors are, in terms of cosine similarity, they're the same vector. So we're trying to bring out any magnitude and just focus on, are they pointing in the same direction? This one, I have B is minus A. So really this time they're pointing in opposite directions. And I get a minus 1. And then finally, just I sort of set it up that A times B sort of gave me 0. And I can get the cosine similarity to be 0. So again, this is just some idea from data analysis. You have two vectors. Maybe, again, I'm suggesting maybe somehow answers to a survey question, and you want to know how similar are two sets of answers. And it is a measure of that, of within data analysis of similarity by and pulling out the magnitude, more about similarity in direction. And it's just very short. This is more comments than anything else. So it's a very short program in R and just playing around, getting used to vectors. That's my real purpose here. All right. Thanks for your attention.